Morning, folks. Quite the turnout this morning. That's no big deal. I swear, today's the last day we're going to talk about tension members. Okay, so it feels like I'm a broken record up here saying we're talking about tension members. This is the last time. And the reason we're going to talk about it one last time is we still haven't talked yet about how we might design a tension member with a welded connection. We've talked about all these limit states. We've talked about yielding, block shear, net section fracture, and the slenderness ratio for serviceability limit states. And we did all this stuff for bolted connections. We designed a bolted connection. And then we started talking about welds for a bit. So we talked about what welding looks like, the different kinds of electrodes and their strengths, the different types of welds we might be used to making and specifying. And then because usually we're going to be specifying fillet welds, we looked at the strength of fillet welds. And then we looked at how fillet welds influence the calculation of the net effective area for net section fracture calculations. So today what we're going to do is we're going to say, okay, well, we know how to design a bolted connection. We've talked about welded connections, and now today we're going to look at designing a tension member with welded connections. Okay, so today is about welded tension member design. The outcomes are basically the same. I mean, the first one is if you're specifying welded connections, you should be able to select an appropriate tension member to satisfy the same serviceability and ultimate limit states we talked about before. It's really not going to be that different from what we did for bolted connections. It's just now we have a welded connection and we need to change how we consider the effects of having a welded connection on the shear lag and net section calculations. What is more new is we know how to calculate the strength of a fillet weld or of several fillet welds in multiple segments and orientations. Now we're going to focus on selecting the size, length, and arrangement of fillet welds so that we can actually satisfy the strength requirements to connect the tension member to a competent gusset plate. Okay, so the same stuff we did in lecture 17, but now we're looking at it with the perspective of having a welded connection. Any questions about these two things before we get into what this looks like this morning? Okay, so it's all the same stuff. So all this stuff is basically the same, right? So the engineer's scope isn't really changing much. The only thing that comes into play a little bit more is you should still have an idea of how the fabricator might connect the section, okay? 80% of the time we're probably going to be specifying bolted connections, but there are situations when you might want to have welded connections. If you're designing a great big truss that's going to be craned into place, you might want to have a welded connection. If you're trying to specify a pre-tensioning mechanism like we had in the school on the north side that I showed you previously, you're probably going to have a welded connection. And so sometimes we'll weld things, and you should know when we're typically going to be doing welding instead of bolting. And then it's estimating the cross-sectional area to satisfy, the gross section yield and net section fracture limit states. So we're going to do the same thing, but we know that welding doesn't take away cross-sectional area unless you're dealing with an HSS and you're slotting it over a gusset plate. But for most sections, we don't take away any cross-sectional area, so that changes things a bit. And then the way that the welds transfer the stresses to the section, that changes the shear lag a little bit. Everything else is the same otherwise. For the fabricator, though, it's a similar but different scope. We're trying to start with a size of weld like we'd size a bolt, for example. So you should be knowing if you're going to be welding in the field or if you're going to be welding in the shop, because that tells you how big a size weld you can make in a single pass when you're doing these kinds of connections. Then you have to develop the connection layout and make sure that the welded connection you've designed still satisfies the tension member and fillet weld limit states, basically weld shear, net section fracture, and block shear failure. Okay, so the scope is very similar, or it's almost identical for the engineer of record, only slightly different here now for the fabricator. So when we're looking at how the fabricator might connect the section, there's really not a whole lot of difference. So if you're doing channels, they're still going to be putting the web against the gusset plate and doing some welds. Flat bars, similarly, angles, one of the legs is going to be against the gusset plate and you're going to be welding it. WTs don't typically get welded. I don't know why necessarily. I think everyone just bolts them. And S16 doesn't provide explicit guidance in determining the shear lag factor for welded WT sections. So you should know some of these things. We already looked at what this might mean for bolts, right? And so basically we said if we're dealing with a bolted connection for any of these typical types of rolled shapes, then we're going to be taking away area for the bolt holes, and that means certain ratios of the net area to the gross area for these different kinds of connections. Again, these are estimated values of the net section factor that would give you the net area if you were to calculate it, and they're a little conservative. So usually you would say, okay, well, if I actually calculated the area of the WT section, it's probably going to be 77, 78, maybe even 80% of the net section, but these are conservative values to use. And then based on how the section is bolted, we'll have a certain shear lag factor. But then we started to talk about these welded connections, and so for a flat bar, right, if we have a flat bar and it's welded by this transverse weld along the edge of the plate in an arrangement that's perpendicular to the applied force, we're not taking away any area for the bolt holes, and we're not reducing the net effective section to account for how the stresses are transferred into the cross-section. So here, this is quite different from bolts. For bolts, basically we said, okay, there's no shear lag, but we're removing maybe 30% of the area. If we have a flat bar and we weld it all the way across, we can get the full net section as effective. And so if you size it for even gross section yielding, you should be able to satisfy the net section fracture limit states even if you, just by providing a transverse weld here. Oops, here. It's not always practical to have that transverse weld, and so sometimes for flat bars we might just weld it in a certain arrangement where we have these two longitudinal welds instead. And again, as the engineer, you don't know L, right? You don't know when you're specifying this flat bar how much weld length they're going to specify. The fabricator is probably going to try and keep that relatively small so that their gusset plate doesn't get too big. And for that reason, I tend to say, all right, well, we're probably going to be mostly in this region. And so if you're the engineer and you're trying to figure out what the shear lag effects might be on this flat bar, or if this was the lag of an angle or the web of a channel, it's reasonable to assume that they're going to at least make the length of the weld equal to the width of the plate. Okay, it would be weird, I think, to see welds much shorter than that. And so what that means basically is that L here is equal to W, and so AN would basically be equal to, or sorry, ANE would be basically equal to 0.75 WT. Okay, so it's most often the case that the lengths of the welds are going to be at least equal to the width of the plate. And that gives you a sense that, okay, as the engineer, I'll think that at least 75% of that cross-sectional area is going to be effective in tension when I'm doing my net section calculations. From time to time, if you're dealing with outstanding legs on channels and angles, you might also have to deal with this. Again, if we stick with the assumption that the length is going to be equal to at least the width of the plate we're connecting, then we can say we're going to get at least 50% of that leg effective in tension when we're doing our net section calculations. And finally, if we think about HSS sections, it tells us here that we have a shear lag factor that we're trying to calculate, right? We looked at this the other day. That's the shear lag factor, 1.1 minus X prime bar over LW. And that has to be greater than or equal to 0.8 AN. And so basically we could say, well, if I'm reading this right, and it's not exactly the right interpretation, but if I'm reading this right, the shear lag factor is going to be at least 80% of the net area. And so I also have to account for the fact that I've got the slot taken away. Let's just say maybe 10 to 20% of the area is getting removed for the slot of that HSS. And then I'm going to multiply that by 0.8. What that gives us basically is a new table we might work with here. The only kind of section that we're actually going to be removing cross-sectional area for is the HSS. And the area we're removing is that 2 times the thickness of the slot times T. We did that calculation at the end of lecture on Monday. And so we're removing a little bit of the net section, and based on my calculations, that tends to be roughly a 10% reduction in the cross-sectional area, so it's not significant. And then we have a shear lag factor of 0.8 there, and that's just the minimum value that we see in that clause for HSS sections. Okay, for all other sections, we don't remove any cross-sectional area to make these welds, and so that means we're preserving the net section, right? So AN to AG is basically 1. We're not removing any area. But based on those assumptions that I had suggested for the different fillet weld arrangements, so for a plate, for example, there's that 0.75. And for channels and angles, they tend to look something like 0.6 and 0.8. And if you want to get those values yourselves, then basically you can just go into those requirements from S16 for the different orientations of fillet welds, for the transverse, the longitudinal, or one-sided. And if you assume L is equal to W for a bunch of different kinds of shapes, you'll basically work out these similar ratios. Okay, so based on the way that the sections are being welded, we're not losing any net area unless we're dealing with HSS. And then we have a different set of shear leg factors that we might be dealing with for welded connections. So we basically said we used to bolt stuff, and that results in certain losses of the net section. And then we have certain factors for shear lag effects. Welds tend to change that. If we don't have a transverse weld, we might be dealing with 75% of the area. For a single weld, we might be dealing with 50% of the area if L is equal to W. That's an assumption. And for HSS sections, we move a little bit of section, and then we take the 0.8 factor here as the minimum shear lag factor. And we arrive at a similar table, but the factors are slightly different. Does anyone have any questions about what went into this table before we continue on? Are there any questions about what this table means for us before we continue on? Okay. So as the engineer, you have to be thinking, first of all, are they probably going to be welding this or bolting this? And then if they're welding or bolting, I want to make sure that I'm accounting for the shear lag effects and the removal of cross-sectional area so that when I give this section to the fabricator, they can make a connection work, right? That's the goal. So we basically have two tables. We've got one for effective area for welded connections, and we have one for bolted connections. Notice here that HSS is not here because we don't bolt HSS sections. It's just not something that's practical to do. These types of sections we can bolt or weld. On the welded side, we lose WTs and gain HSS sections. Let's just say we were dealing with angles or channels or flat bars. Those are the ones that we could either weld or bolt. Let's say you have no idea, okay, well, there are 4 local fabricators, these folks like to bolt things, and sometimes these folks like to weld things. I have no idea who's going to be building this. If I look at this table, L 0.48 net area of net effective area to gross area, channels 0.6 and plates 0.7, and then I come to the welds and I see 0.6, 0.6, 0.75. Which of these two tables do you think I should be using if I don't really know if they're going to be welding or bolting that tension member when they go to build it to design my tension member? Should I be using the welded tension member table or should I be using the bolted tension member table? Any ideas? Why would I use the bolted one? Yeah, basically, right? Like, if you look at the ratios here, well, remember, A&E is a direct, indicator of the net section strength. The smaller A&E is to AG, then the smaller the net section fracture resistance is going to be. If we look at 0.48, 0.6, and 0.7, and we compare that over here to 0.6, 0.6, and 0.75, if we're welding, we can almost always get more of the net effective section or more of the gross area effective in tension when we're dealing with net section fracture calculations. Okay, so if you have no idea what they're going to do, you want to take the conservative perspective and design it as if they could either bolt it or weld it. And if you're going to say maybe they'll bolt it, then you're going to want to deal with this table because that will give them enough area to bolt. If you don't deal with this table, especially for angles, like if you say, okay, well, angles, I'm going to use 0.6, that kind of ties the fabricator's hands. They're going to have to, for the most part, bolt that or weld that tension member. Either that or they're going to have to make sure that if they bolt it, they have at least 4 bolts in that connection so that this number here could perhaps go up to 0.8, and then we'd get an A&E over AG ratio of 0.64. All I'm trying to say here is you have to kind of maintain some flexibility. You have to give the fabricator the option of bolting or welding, and to do that you want to make sure that you're giving them enough area, and so most of the time that means we're basing these calculations off of a bolted connection. So basically we said we've got some factors for welded connections, we've got some factors factors for bolted connections, we want to give the fabricator flexibility to do either, and it's more conservative to design based off this table for bolted connections. Are there any questions about that before we continue on? Okay. So this process is more or less the same. We're the engineer and we're saying, okay, I have to satisfy gross section yielding. I can't, as the engineer, satisfy net section fracture, but I have to be a smart engineer and give the fabricator a chance at satisfying the net section fracture resistance. And so I'm going to estimate the effective net section using these two factors. And I'm going to throw my hands up when it comes to the welds or block shear, because I have very little or no control over block shear and weld resistance calculations. That all sits with the fabricator. And even if we're doing a welded connection, we may still want to use the bolted values for NSF and SLF here for doing that kind of thing. So if we're coming back to our example building here, and I'm going to say, all right, well, we already designed this brace down here for a certain force. We designed this as a bolted connection. We looked at a flat bar in class. The flat bar is pretty big. I probably wouldn't recommend using that flat bar in an actual practical application. But you could use a WT or something else, and a WT is selected in the example notes as an alternative. Today we're going to look at a different part here, and so we're actually going to look at the top member here. Okay, so we're going to look at the top brace. Again, we're just going to assume that we still have this tension-only bracing and not this zigzag configuration. And maybe from the STAD Pro model, based on that same load case, dead plus earthquake plus live plus snow, we're going to say we got a factored tension force of 983 kilonewtons for that particular brace. And what we're going to do is we're going to go through the same process. I'm doing this for a different load because we'll get to see a slightly different section. If I had said, okay, well, let's design the same brace and assume that we could have either welded or bolted, we'd just be doing the same exercise again, and that's boring. So let's use a different factored load for a different brace and repeat the process and see if we come up with something slightly different. Okay, so part one here is to select a cross-section that will satisfy ultimate serviceability limit states that we can control as the engineer. And we'll check that what we selected would also work for welds. So if we check for something for bolts, we'll also make sure that it would be reasonable for welds, which 98% of the time it will be. And then the engineer, as the fabricator, will go in and say, okay, for this brace, for this force, let's arrange some welds and come up with an arrangement that will work in terms of the fillet weld strength and the net section fracture resistance. Block shear is not going to be super important for us in this case today, but I think I show you the calculations in the example notes. This is one of those situations where, for the example we're going to be looking at, block shear is very rarely, it's going to rarely govern. Okay, so it's not super important, but I do want to show you in the example notes just how a calculation might, how a block shear calculation might work for a fillet welded tension member instead of just a bolted one. So we're going to pick a channel that will work for welds and bolts. We're going to then design the connection using fillet welds. Are there any questions about what it is we're trying to accomplish here in the example before we get into some of the calculations? Okay, so we basically have to come back, right, to the same stuff. The first thing we're going to do is we're going to specify the type of connection we're going to be using, or at least the arrangement of the connection. So we're going to use a channel. Okay, so we'll sketch what we think this channel is going to look like. The top of the flange here, something like this. Right, we'll remember that channels are these types of shapes. Right, something like this. And we're going to connect that to the gusset plate down here, something like that. And as the connection designer, or as the engineer, I guess I should say, as the engineer, you're going to say, this is what I think the connection is going to look like. If I wanted it welded, I would say something like this. I would point to this, and I would put two fillet welded triangles here, but I'm not going to specify the size. Okay, so if I wanted them to weld this for sure, I would specify that I want fillet weld here and fillet weld here, using this symbol for this side and the other side of the arrow. And I'm going to leave it blank, and I'm going to say, size and length of fillet welds to be determined by the fabricator, something like that. If I wanted them to bolt it, then I might just say, okay, well, I'm going to have 4 bolts or something like that. And you might give them the option. You wouldn't say both bolts and welds. You don't normally. You can say fabricator can either weld or bolt based on the cross-sectional area provided. Okay. So the gusset plate's going to be something like this, and we're either going to weld it or bolt it, something like that. And we're going to focus on welding it, but we'll look at the implications of whether we choose to have a bolted welded connection. Any questions about why this connection might look something like this before we continue on? Yeah?
Why did you choose the channel?
I'm showing an example channel. And so channels are, it's not uncommon to use channels as a tension-only brace kind of section. We'll see satisfying slenderness with channels is quite difficult because they tend to be quite floppy. So we might have to specify some kind of welded connection like they did for the flat bar in that school I showed you. I'm just picking it to demonstrate how you might design a channel if you were to pick a similar brace in this situation. It's probably a little bit better than a flat bar, right? It's almost a flat bar, except it has 2 little pieces on the other side here, right? The 2 flanges to help stiffen it up a little bit. A channel, double angles, HSS, flat bar, you could pick anything. And for the most part, it's either going to be the company you work for has certain design practices, or the client you're working for likes things built or designed a certain way. And so normally, as the engineer just kind of plugging through some of the calculations, you're not going to be having too much of a choice as to what channel or what section you're working with. Usually that'll come from either the senior engineer for the specific application or from the client. Cool? Anything else? Okay. So we're designing a channel, and we're going to either bolt it or weld it. We're going to look at the fabricator welding it, but let's come back here and say, okay, well, we need to figure out how much area this channel is going to have, because we need to basically see what by what is going to work for us here. And to do that, we do the minimum calculations for gross section yielding and the minimum calculations for ultimate strength of the net section. So maybe I'll start on the new slide here. We're going to say, oops, not that. A min for gross section yielding is TF over phi Fy. If we're specifying a channel, what material grade of steel are we most likely to specify as the engineer? Is it ASTM A992 grade 50? No, that's for WTs and wide flange sections. For channels, angles, flat bars, we do fabricate those in Canada. And so we're going to specify for this channel 350W steel. Okay? Again, not a huge difference. The fracture strength's the same, but the yield strength is slightly different. So TF is the 983 kilonewtons. I'm just going to add a 10 to the 3 there to get it into newtons, so that when we divide by MPa, we get our millimeters squared back. We divide that by 0.9 times 350 MPa. And if we do that for the channel, the minimum area that we need is 3,121 millimeters squared. Okay, so we've done that before. Are there any questions about that before we do the other minimum area calculation? Okay. So we're also going to have to do this for the net section, for net section fracture, and we're going to basically say, okay, we'll estimate NSF and SLF, which are parameters we also add to STAD Pro, so that STAD Pro can pick some stuff for us. And again, if we come to the bolted connection table, we're going to see that we might have 0.8 and 0.75. That gives us 0.6. Whereas if we're welding it, we have 1 and that should be 0.8. So our channel might be a little bit heavier, if we go with a bolted connection, because we get 0.6 versus 0.8 for our channel based on this calculation. Now, we could sort of say, well, let's make the most efficient design, specify a transverse weld so that all of the web is effective, and then we just have to worry about the flanges a little bit. Like I said, it's more common to have two longitudinal welds. And so it's most likely that they're going to do something like this. And so we'll give them enough steel to at least be able to do that. Okay, so that's where the 0.8 here comes from. But if we want to give the fabricator some flexibility, we say, well, we're not sure if they're going to weld it or bolt it. And we look at this table here, the 0.8 and 0.75, roughly giving us 0.6. That's going to require more steel in the channel. And so if we want to give them the flexibility to bolt, then we're going to use these factors for bolting instead of the factors for welding. Right? They're going to result in more steel in that channel, and that will give them the flexibility to choose what they want. Okay, so very similar steps here, 983, 10 to the 3 newtons, divided now by some other stuff. FEU is 0.75, FU is 450 MPa, and then for channels we're using 0.8 and 0.75, and that's going to give us a a minimum gross area required of 4,854 millimeters squared. Any questions about that calculation? What does that number mean? Between those two numbers, which one is the one that we need to work with when we're specifying the channel section? 4,854. Basically, we need more than 50% more steel, right? We need roughly, what's 1 over 0.6? Like almost 60% more steel in the cross section here. And so we basically work with this 4,854 millimeters squared number. Okay, so we need a channel to have at least this much steel in it. So what do I do here? Do I need to proportion a cross section like we did for the flat bar in lecture 17, where I said, well, I need to come up with a custom bar, width thickness ratio, blah, blah, blah. Do I need to do that for hot rolled channels? No, what do I do then? I go to the handbook, right? Normally I bring the handbook with me and I put the camera on my iPad and kind of show you the process. I forgot to bring the handbook. Do you have the handbook with you? I'll borrow that if you don't mind. Oh, this one's closer. I'll borrow this one. Thank you. So let's try that then. My camera work is a little shaky, so please bear with me for this one. Let's try it. Okay, so we're in the handbook, right? So we're down in the 4-page. Oh, that's not where we want to be. We want to be back in section 6. Right? So section 6 is where we have all the different section properties. So here's some wide flange shapes. That's not what we're designing with. Here's some angles. That's not what we're designing with. Structural tees. That's not what we're designing with. Standard channels. Okay, so over here we're dealing with standard channel shapes. There's also some miscellaneous channels on the next side. We're not going to be using those. Standard channels are more common. And basically what we want to do is we want to pick the least weight channel. And so we're going to start over here, right? And we're going to start with the smallest channel, and we're going to see how much area is in that channel. Okay, so C75's the heaviest one. We only have 1,100. We basically go up this table until we find a channel with enough area in it, right? So here we're almost at 4,000. We need 4,800 and something. There are two channels. There's a 250 by 37 that has 4740. There's also this one that has 4740. And then the next biggest one are the two that have 15690 and 5690. Okay? So I need 48 something, but again, this is pretty close, right? 4,740. That's pretty close for an area of the channel. And I already know that the values I use for NSF and SLF are probably quite conservative. Okay, so I'm actually going to pick one that has slightly less area than I need. I know that the fabricator, if they know how to do engineering, can make this work. I'm going to be short by like 2 or 3% of the area, but they can certainly make that work. Okay, so I don't remember what I actually picked. I think that's what I ended up picking. So this is what I end up picking. I pick a C250 by 37. That's going to give me 4,740 millimeters squared, and so that's the channel that I'm going to work with. Okay. Are there any questions about how you might find a channel or another section in the handbook that might work based on the minimum area that we need for the tension member resistance? Okay. So we're going to basically say on our sketch, or maybe I'll draw this. So here's our brace frame, and I've just got a little bit of I'll just make a break line here. So we're going to specify basically C250 by 37. Our factor tension force is 983. I'm probably just going to write this as TF is 990. Okay, and as long as they know that it's tension-only bracing, they're going to know they're not designing it for compression. So TF, the factor tension force that we're designing for, is 990. The engineer is usually going to round it up a little bit. Very rarely would you see 983 written on the drawings. And that's the information that the fabricator is going to be working with to try to make a channel work. Okay? In this case, I didn't look at the radius of duration. I probably should have, but I already know that we're not going to be able to make slenderness work here. The radius of duration for this section is quite small. The slenderness ratio is probably going to be 400 or 500. So I'm going to need to do something to take the slack out in the field, and I'd specify that on the drawings. Are there any questions about how we settle on this information and why this is information we pass along on the drawings to the fabricator before we go looking at what the fabricator is going to do with this? Any questions? Okay. So, fabricator decides I'm going to weld it. And when we look at welds, we've looked at the strength of welds, right? The first job of the engineer is to specify the size and the length of weld to satisfy the shear strength limit states for the actual weld material. Okay, so I need to make the weld strong enough. That's based on this equation. And for welds in pure shear, this is the expression we use. And if the welds are in tension of any kind, so in this case, we looked at this example the other day where we had a transverse weld. If we have a transverse weld, we have to modify the strength to account for the fact that there's weld that's going to fail in tension versus shear. That changes the strength a bit. And we might also have to consider, if we're using both, a transverse weld with longitudinal welds, we're going to have to account for the fact that the transverse weld is going to go before the longitudinal welds fail in direct shear. So what does this mean for us? How could we figure out, first of all, what we're going to do as the fabricator to weld this? And depending on what we do, how much weld we need. What do you think we could do to figure out what the weld should look like as the fabricator? Take 30 seconds, maybe a minute, talk with the person next to you or think about it. It's also not a bad idea to have a little bit of a break from me yammering on for a little bit. Take a break, talk about what you think you might do as the fabricator to figure out what this welded connection should look like and how much blue or red weld you might need. We'll come back to and talk about that in about a minute or so. All right. That's probably good enough. I know this example is pretty insane, crazy, and hilarious, right? We've got a decision to make as the fabricator. What do you think the first decision we should be making will be before we start deciding on lengths and size and stuff? What's the first choice we need to make? Any ideas? Sorry? So, yeah, that's the first one. Is this going to be a field welded connection or a shop welded connection? That's going to have implications on the process, maybe how many welds you specify, because there might be different positions for that welding, and the size requirements, right? You can only weld up to 6 millimeters in a single pass in certain situations. Depending on the thickness of the steel, you might need 8, and if you need 8, that has to be done in the shop. Otherwise, you need to bolt it. So let's just say they're installing this in the field in a similar manner as the flat bar in that school across the river. We're going to field weld this. That means we need to have fillet weld sizes in a single pass no bigger than 6 millimeters. We can build them up to be bigger using 6 millimeter welds to make 8 or 12 or whatever, but the maximum single pass weld size will be 6. What else do we need to decide? From my perspective, I'm going to say, are we only going to do red welds, or are we going to do red and blue welds? And I don't mean like it's the color of the welds. What I mean is, are we just going to have longitudinal welds in the connection, or are we going to pair up those longitudinal welds with a transverse weld? Okay, so first question is, do we do 3 segments, or we just do 2? So depending on which option you choose, you can do either. The first situation, you say, I want to do just longitudinal welds. I'm not going to have a transverse weld. If you don't have a transverse weld, then you don't need to reduce the strength of any of the welds by that MW factor. And all you need to do is figure out what your minimum weld length is. So you say, first of all, let's just say we're going to try 6 millimeter welds. And let's just say we're going to do a single pass. D is 6 millimeters. From there, you can say, okay, if I know I'm going to use 6 millimeter welds, I'm going to be able to calculate how much length I need. Right? So from this equation back here, we basically have 0.67 VW multiplied by D over root 2 LW XU. For 350W steel, we're going to be using E49XX electrodes. And so we know XU. We know VW, we know 0.67, and we've just selected D to be 6 millimeters. So we can back calculate that and say, okay, LW is going to be the factored force divided by all the other stuff if we rearrange that equation to say VR needs to exceed TF. Right, so here we know TF needs to be less than VR. And if we rearrange that equation, we get something like this. This little part in the denominator here, 0.67 VW dxu, if you look at what you're going to get for units here, you have MPa times the length, which is a force per millimeter or per length. This is basically going to tell you the shear resistance of X size weld or D size weld per millimeter. And I'm going to call that in this course little VR. Okay, so it's a little shear resistance. It denotes the shear resistance of that weld per millimeter. And the reason I'm going to do that is because the handbook gives us tables for that, so we don't have to do the calculation every time. So that's one thing you can do. I'm going to figure out what the minimum weld size is, and I'm going to say how much length do I need, and that's if I'm going to do longitudinal welds only. If I want to pair longitudinal welds with a transverse weld, there are 2 things happening. One, I've got 2 different segments I need to consider the strengths of. One of them is going to be a bit stronger than the other in the actual resistance, because it's going to be more in tension than shear. But I also have to account for the reduction of the strength of the longitudinal welds. Right? That transverse weld is going to fail first. The stress on the longitudinal welds will not have reached the ultimate strength yet. And so that's what MW is in here for. So if I already know I'm going to have this weld here, the blue one, right? I know if I'm going to have this blue weld, I pretty much know what that length's going to be. I'm not going to just be like, oh, I'll weld half of this. If you're going to do a transverse weld, you're going to weld the whole thing. And so you know what LW is already based on the size of the section. So for our channel, for example, that's 254 or whatever it is. And so I already know how big that weld is going to be, and I can calculate the strength of that weld. Right? So I can calculate the strength of the fillet weld in tension. This is basically VW AWXU. 0.67 gets multiplied out by the 1.5. So those 2 terms kind of go away. and we just have feed WAW XU. And again, I'm going to use this little term. Whoops, why is my pencil not working anymore? Oh, it's unscrewed, that's why. VR, a little VR again for that particular weld. So I already know how much strength I can get out of the transverse weld. And then I just need to decide how long are the longitudinal welds going to be, right? LW, or just L, I guess that should be L, because L plus the other one's going to be LW for the longitudinal welds. And so if I know how strong the transverse weld is, I say, okay, that deals with some of the factored tension force. And the difference now between the factored tension force and how much strength I get from the transverse weld, I have to make up using the longitudinal welds, but it's reduced by that 0.85 factor. If I use the little VR values, I've got a VR for the welds at 90 degrees. I've got a VR value for the welds at 0 degrees. And I can pull these from a table that I'll show you here in a second, and I can use that to calculate the length of weld required. So we've got two options here. We can do only longitudinal welds, easiest, and we could do transverse and longitudinal welds. When we do transverse welds, we take out the strength of the transverse weld from the TF. The remainder has to be made up with the longitudinal welds, and that strength is reduced to account for the fact that we've got welds at multiple orientations. Are there any questions about which of these two expressions or when you'd use them before we continue on with the example? Okay. So what do I do first here? I always forget what I decide to do first. Let's start with, even if it's not in there, we can do it anyway. We'll start with just longitudinal welds. Okay, so we'll start with just this part, and we'll see what happens. How long do these welds need to be if we just do longitudinal welds? There are some tables in the handbook, as I was mentioning before. So table 3-24 gives us the pure shear strength of fillet welds for different sizes, for different weld electrode strengths. And so you might have 43XX or 55XX or 62XX. Bolded is 49 because it's commonly used, because 350W steel is commonly used. 490 is the matching electrode for 350W steel, and as long as you use this, then you don't need to think very hard about it. So basically it says for different fillet weld sizes, what is the strength per millimeter? We are using a 6 millimeter weld, and so the strength of a 490 electrode in 6 millimeter fillet weld size, we get 0.933 kilonewtons for every millimeter of weld in that connection. So that's great for fillet welds, 490, for pure shear. We also have a table here for 490 electrodes, or E49XX electrodes, at different orientations. Okay, 0 is bolded because it's most common to have longitudinal welds. There's our same 0.933 there. And we can also use this table to say for our transverse weld, theta is 90, and so little VR for the 90 degree weld is 1.4 kilonewtons per millimeter. Okay, so I don't need to do very many calculations, phi, W, AW, XU. I just have the factored resistance per millimeter in this table, and that can help me do some design a little bit more quickly than crunching everything out in the calculator. Okay, so two tables here, one for different electrode strengths and pure shear, one for the same electrode strength for different orientations, and we can use them to pick values for little VR to do our design. Are there any questions about how to use this table before we try it out? Okay, so let's try this then. We're just going to use longitudinal welds, okay? Which basically means we're going to take our channel. It's on the gusset plate like this, and we're just going to do this and this, and we've already decided on the weld size. We'll denote that as 6 and 6, and then it's our job here. What are these numbers going to be? These are the length of weld on each side. These two numbers added together should give us the total weld length that we need in the connection. Okay, so basically, we come back here, and we're up here. This is the longitudinal welds only approach. the minimum total weld length I need is going to be my factor tension force divided by the shear resistance per weld that I have in my connection. Okay, so I'm using 6 millimeter welds. I can come to either table, and I'm going to see the little VR is 0.933. So the total weld length that I need minimum is TF over little VR. That's 983 kilonewtons divided by 0.933 kilonewtons per millimeter. And if I do that calculation, those of you with a keen eye will see we need a little bit more than a meter of shear strength there. So where's my option 1 here? I know it's here somewhere. There it is. So the total weld length that I need is 1,054 millimeters. Okay, so I have a factored strength. I've got 6 millimeter welds. They give me 0.933 kilonewtons per meter of strength. I can use that to figure out how much total length I need. Any questions about that calculation before we dig into how that plays out for us here? Okay. So what does that mean for this? We need 1,054. Do we say 1,054, 1,054? What do we say on this arrow here? Yeah, so I mean 527, we have 2 welds, right? This is L, the total length of the welded connection. But LW here for us is how much total length of weld we have, right? So here, L is equal to LW over 2. So in total length on each side, we really only need 527 millimeters. Okay. So I would never specify that on the drawings. I would just say 530, right? And I mean, getting a welder to get exactly even 5 millimeters can be difficult sometimes, but getting them to get exactly 527 millimeters is a different story. So basically I'm going to come in here then, and I'm going to say, all right, these need to be 530 and 530. And then I need to check whether or not that's going to work in terms of the section strength. Okay, are there any questions about why we ended up with this welded connection arrangement, or where these numbers came from before we try and quickly squeeze in a net section resistance calculation? Okay. So 6 was just like, I can't do more than 6 in the field. Okay, 6 millimeters is the size. It's always more efficient in terms of the weld material to use a smaller, longer weld than a bigger, shorter weld. Right, so if you did 12 millimeters, you double your strength, but the volume of weld and therefore the labor you need goes up with that squared. So you need 4 times more weld and 4 times more labor to provide the same strength of weld that's half as long. So in terms of labor efficiency and material efficiency, longer, shorter is better. And the biggest one we can make is 6 anyway in a single pass, and so that's why we chose that. Any other questions? Okay, so we'll go through this as best we can at least. And so we're basically going to say, okay, we need to check this now. And we need to check basically the net section. And we need to consider what the net effective area is going to be in this channel section. Okay, to do that, we'll remember that we've got basically a couple flanges here. I'm probably not going to get all the way through this, but it's in the example notes. And I've got welds here and here. And I already know then that I've got 2 rectangles here that I can call AN3s. And then because I've got longitudinal welds, I have an AN2. And so to figure out the total net effective area for this, we need to come back and we say, okay, we have no transverse weld, so there's no AN1. We have a length of weld that is actually more than twice the width of the section. Our channel here, whoops, our channel width is 254 millimeters. The length of weld is 530. So when we come back here, we've got an AN2. So our effective area is the full channel web area, W times D. So AN2. is the width of the depth of the channel times the thickness of the channel, which is D and W. Then our AN3s depend on some other properties. And so AN3, we've got two flanges that are connected by a single weld. We have a length of weld that's greater than W. And so we're using this 1 minus X bar over L calculation. And so AN3 is 1 minus X bar over L. And in our case here, the width of the plate is going to be B minus W. It's the width of the flange minus the width of the channel web. So W is going to be B minus W. And then that's going to be multiplied by the thickness of the flange. In that case, plus we have two of them. X bar over L here is going to be B minus W over 2 plus W. And so we're going to end up with an AN2 and an AN3 that are calculated in this way. I'm not going to try and stretch this out in any more detail because I know you're going to get to the next thing here. But this example is continued in a couple different ways. So I've done the net section calculations in the example notes. I've redone it with a transverse weld, so you can see how transverse welding affects the connection arrangement. And I also did it with longitudinal welds that are bigger, so you can see how that changes the calculations as well. Okay, so basically you should be able to do the same stuff from lecture 17, but now considering welded connections. And that's basically it for tension members now. We can finally move on to talk about something way more interesting, which is compression members. Again, we're not here Friday, right? So we'll start the unit on compression members when we're all back here on Monday. Does anyone have any questions about anything that we've talked about today before we wrap up lecture this morning? Okay. Have a great weekend then, everyone. I'll see everyone on Monday.